I would like to introduce you to the concept of related rates. Now, in front of us we have a right triangle. The legs of the right triangle are signified by x and y. The hypotenuse of the right triangle is r. And in a related rates problem, what we're assuming is that each of these quantities can change, that x can change and y can change, and if x and y change, then that means that r can change also. So it's possible that all three of these variables, x, y, and r, and the quantities that they represent, are functions of time. So we could say that x is a function of time, y is a function of time, but a different function of time than x, and r is a third function of time, which is different than the other two. So we are understanding that these are all functions of time. Now, we don't know explicitly how they're related to time. All we know is that they are related to time. Now, one thing that ties all three of these variables together in this right triangle is the Pythagorean theorem. So we can say that x squared plus y squared equals r squared. And so we know that that is absolutely true. So what we're going to end up doing is we're going to take the derivative of each of these quantities in that expression, x squared plus y squared equals r squared. Now, the derivative of x with respect to time, let me back up there for just a moment. The derivative of x with respect to time is going to be a derivative. And another way we can write that is just as x prime. And a derivative of y with respect to time, that would be g prime of t. And we're just going to write that as y prime. And then finally, the derivative of r with respect to time is going to be something like h prime of t, but we're just going to write that as r prime. So when we take the derivative term by term in the Pythagorean theorem here, first of all, we're going to use the power rule. So the derivative of x squared is 2x, but then we have to multiply by the derivative of the inside function. And since we're saying that the inside function x is a function of time, we know that that's going to be x prime. And then the derivative of y squared, well, that's going to be 2y times y prime. And the derivative of r squared is going to be 2r times r prime. So we can simplify this expression by dividing everything by 2, and we get x times x prime plus y times y prime equals r times r prime. Okay, and so anytime we're using a Pythagorean theorem, a problem that's based on the Pythagorean theorem, we can write an expression like this. Now, sometimes one of these variables, x, y, or r, may be constant, right? In other words, maybe, for example, we've got a ladder tilted up against a building, and the ladder slips. And as the ladder is slipping, x will change and y will change, but r is going to remain the same, which means that on the right side of our Pythagorean theorem derivative equation, we would end up with 0 on the right side of the equation. Another example is if we have a plane flying toward a ground base, and the plane is at an altitude of y. If the altitude remains constant, then as the plane approaches the ground base, which would be in the lower left-hand corner of the triangle, r would change and x would change, but y would remain constant. And so y prime would be 0, and that would change our Pythagorean theorem derivative equation. So how we do that then depends on the type of problem that we're dealing with. Now here's another example of a situation in which we might encounter related rates. Suppose we have the area or not the area rather, but the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. The surface area of a sphere, which we'll call capital S, is equal to 4 pi r squared. So it's good to know these formulas. Now, both the volume, for example, if you have a balloon and you're blowing up the balloon and the balloon is spherical, so as the balloon increases its volume or changes its volume, okay, its radius would change also, and that would be dealt with by taking the derivative of the volume equation. And so we could say that dv dt, the rate at which the volume changes, would be equal to 4/3 pi, and then we would multiply by the derivative of r cubed, which would be 3r squared times dr dt. And then simplifying that, we would get, the 3's will cancel, and we'll get 4 pi r squared times dr dt. So what we mean by that then is that the rate at which the volume changes is related to the rate at which the radius changes, and that makes perfect sense. And we'll see how this works out in future problems. Now, regarding the surface area, likewise, as the radius changes, the surface area will change. So we could say that ds dt would be equal to 4 pi times the derivative of r squared, which is 2r times dr dt. And then simplifying that, we get ds dt is equal to 8 pi r times dr dt. So this is another way in which these rates are related. Now, if we're talking about the same balloon, we know that dr dt for the spherical balloon is going to be the same as dr dt for the rate at which the surface area changes as well. So that's how the rates are related, which is why we call this related rates. Now, a third example, you might have something like the volume of a cone. And the cone has a radius, and the cone has a height. Okay, so the volume of a cone is actually related to the volume of a cylinder. The volume of a cylinder is pi r squared h, and the volume of the cone is 1/3 of that. So it's possible that r would be a function of time, but also h would be a function of time. So what that means is that both if r and h change, then v, the volume, will change. So we could say something like this. We could say the derivative of the volume, or the rate of change of the volume with respect to time, is going to be equal to, now I'm going to factor out the 1/3 pi, and then we take the derivative of r squared h. Now, since we know that r and h are both functions of time, that means that we have to use the product rule and the chain rule. So if we take the derivative of r squared, first we get 2 times r times dr dt times h, and then if we then take the derivative with respect to h, we're going to get r squared times dh dt. And so we might simplify this a bit. 1/3 pi, change that pi there, make it look a little prettier. And then this is going to be multiplied by 2rh times dr dt plus r squared times dh dt. Now, so all three of these examples are ways that we can say that the rates of change of some of the variables are related to the rates of change of other variables. So like in this problem, if h changes, the height changes, and r changes, then that means that the volume has to change as a result. So those are related rates. So we'll continue to see how this works in specific types of problems.